The title of the talk is Shared Authority Control of a Mobile Collaborative Robot Assistant. A little bit about me, actually, there's no need because Mark already explained a lot. I work at IIT, and this is the part of the team actually that we work on different European projects, including the ERC, Project Ergonomic, Horizon 2020 Sophia, and the recently concluded Amazon Research Awards project, ELON. So the topic of the workshop today is, of course, shared control, and there was a really nice video describing what shared control is by Paulo's, in one of the Paulo's presentations. And of course, this concept has been long recognized also in the robotics and automation society. For instance, Paul Fitt's perspective of shared control in 1951 already was envisioning bringing humans and robots together to create really flexible, smart, and reconfigurable systems that humans and robots can work. And at the end of the day, you have the best features of each component. As we know, perception, let's say supervision of the human, and also the endurance, speed, and power of the robot. And this has been a very nice and long-lasting, let's say, concept in robotics already for now. And where these systems can be applied and deployed today, of course, especially what my research is concerned, when we mostly focus on industry, we have a lot of problems to respond to. For instance, one is the aging workforce, that every year there is much less people joining the workforce than the ones actually retiring from the workforce. For instance, by 2020, we will have 8.3 million labor gap. There's a lot of other problems, for instance, due to the manual handling of awkward size objects or heavy objects. We have work-related musculoskeletal disorders, which cost billions, hundreds of billions actually each year in Europe. I'm pretty sure these numbers are as bad as this in other, let's say, countries as well. Production flexibility is also something that basically we would like to increase by creating shared autonomy robotic system. But why we haven't been able to see such systems already functioning in, let's say, industrial applications and similar? So on the left side, what you see is a robot with the potential of human-robot collaboration, shared autonomy, or robot-robot collaboration, but they are doing the tasks that industrial robots were supposed to do, like pick and place in softer caged spaces. When we want to bring humans and robots together to work, it's also good to remember Fabrizio Flacco. I always put his video here. When we bring humans and robots to work, we usually try to avoid any contact between the two. So therefore, these two concepts do not let us to exploit the full potential of collaborative robots. We need to really make sure that the people can actually, people and robots can actually work together. So the vision we have is to create, we have three enablers, right? We have humans, we have robot and environment, and products, and we have the robots. So we want to improve the adaptation of robots to the environment through some feedback, adaptation of humans and robots and vice versa, and also adaptation of robots to the environment. To go in detail in some of these aspects, I would like to highlight some of the works we've been doing. Of course, just having the idea of Paul Fitts in 1951 is not enough. Now, to be able to translate it in robotics, we need to actually understand how we can take it to the next level. For instance, now we can use the good principles and really rich principles of lean manufacturing that we want to eliminate waste, avoid superburden, or prevent unevenness or variations. These are concepts that has been with us for a long time, but we don't see their good integration in robotics field. For instance, what it means as a robotics to me, it means that if I have agents like robots, humans, different robots, I need to assign the tasks to each one of these agents based on their capabilities, based on their speed, power, ergonomic needs, dexterity, and all that. One example will be basically if we can decompose each atomic action of the task to complexity of the task. For instance, robots can do complex tasks, yes, but might take much longer to do it as if a human does it. And we have agent dexterity, which can be basically the workspace of the person, force production, and things like that. And the agent effort, which at the end of the day, how much effort you spend each agent to perform a task. If we bring them in a unified, let's say, control framework, what happens is that you can assign the roles between humans and robots. As you can see here, the robot decides which tasks are the best to be performed to minimize the fatigue of the person, in the meantime improving productivity. Those examples are large movements of within the workspace, carrying heavy loads, dealing with the sharp objects. But in the meantime, if you have a scrolling task, which is really complicated for a robot to do, otherwise you need really special grippers and so on and so forth, you can assign it to the human. To make this talking, this communication intuitive, we created an augmented reality interface only to provide some feedback and to get some really intuitive comments from the human. For instance, if the person is like, in parentheses here, the robot is gravity compensated, waiting for the human to do this, let's say, complex assembly task, complex for robot assembly task. And when it is done with a simple gesture, the robot basically considers the task achieved and therefore goes and waits for the rest of the comment. This is basically one topic that we can bring a simple example of what it means when you want to have humans and robots working together. So now that we have this framework, we can actually move it to the next level, which means that we can ask robots to help humans to improve their body states, dynamic loading conditions, and things like that. For instance, the robot on the left side can trigger and understand what is happening in your body poses in terms of, let's say, loading, vibration, and forces, and things like that, and can actually help you, given the constraints, to do your task in the way more ergonomic and productive way. So, of course, we need models, we need some optimality, we need some learning. Here we are actually relying on humanoid dynamics that we apply to the human understanding of interaction between humans and the external world. For instance, if you write the dynamics of the interaction for the person without interacting with the external world, and basically if a load appears to be dealt by the human, we see that of course the center of pressure displaces, and as a matter of fact, through some, let's say, math, if we subtract these two, we can understand what is the loading effect of this external load on the body joints. So basically, by knowing the center of pressure displacement and also by actually being able to measure the external forces through the force plates or basically the sensor insole. So this is one example. If you're interested, you can read the papers how we do that. Basically, overloading torques in real time, which is the most important factor for us, are estimated across body joints by this reduced complexity technique. So this reduced complexity doesn't need the inertia parameters or gravity parameters of the body limbs, and this makes our calculation way more real-time and way more efficient and personalizable to each subject. Now that we have this model, we can actually set up an optimization routine that you can see here, where the robot trajectories can change given the constraints of the task, joint limits, human stability, and all the constraints that we might have to minimize the loading of the person and to satisfy any other objective functions that we have. Let me give you a simple example. For instance, here in a simple handover task, out of infinite amount of locations that you can hand over, there is one that can be optimum in terms of, let's say, loading. If this happens hundreds of times per day and you can multiply it over the years, this loading can be really dangerous, right? But you can actually reduce, let's say, up to 90% up in shoulder and up to some 60%, I think, 62% in shoulder and elbow. And these are the EMG values that actually tell you that this is actually increasing depending on where you hand over the. If we move to way more complex tasks, for instance, co-manipulation, where so many other dynamic aspects come, we can extend our model to also improve the force production capacity of the person through really nice robotics features and robotics tools that we have, force manipulability, system manipulability, and things like that. For instance, here, we have another objective in our optimization, which tells you that not only minimize the overloading joint torques, but also optimize and maximize as much as possible the force production or kinematic, let's say, manipulation capacity of the person when performing the task. And you could see here from A, which the loadings is high, comes to B and B, which is basically where the loadings are low but manipulability is bad, and C is the optimal configuration, which optimizes both cases. We actually built on top of this shared autonomy, and we actually embedded some, let's say, more elegant features, more smart features, so that the robot, by looking at the skeleton of the person, this time we use only the vision system to estimate the load of the object, put it in the model, and also through some visual feedback, we could provide some means of what happens at the loading level. So if you change hands, if you move in a space, the vision system is highly adaptable, and the control system and the optimization system is highly adaptable to respond to the person's need, always ensuring that the task is performed in the most ergonomic, productive, and fastest way possible. Of course, this goes all the way, and if you're interested, you can see the results. And this was a winning application in KUKA Innovation Award 2019. So not only in the shared control, we care about the instantaneous effects and states of the robots and the humans, but also the cumulative effects across time can be also important. For instance, if you're doing lightweight tasks with robots, such as painting, such as, let's say, I don't know, carving, this can across time increase, let's say, the risk of injuries in different body joints. You can see here the circles are getting orange and then red across time, saying that there is high risk if you continue doing that. So, and the robot realizes that you want to stay in that point for a longer period of time and brings you to the most convenient configuration, enabling you to do the task. Of course, just to show you that the system is whole body, we did in another configuration. This time the ankle and the hip was being loaded, and the robot, again, by calculating the fatigue, anticipates what would be the best posture if you want to stay in that particular area for a longer period of time, and optimize it for you to bring you in a really good condition. So far, I talked about the fixed-base robots. To bring you to the real title of this talk, which is the new mobile platform that we have developed. As we all know, fixed-base robots are extremely valuable, but when the locomotion is required, then you have way more flexibility in any, let's say, production or service application that you would like to have. And also in, let's say, Greek philosophers always has been saying that which is in locomotion must arrive at the halfway stage before it arrives at the goal, which this slide counts halfway in my presentation as well. So to respond to this, we created MOCA, which stands for Mobile Collaborative Robot Assistant, which is the integration and customization of some robotic components. This video only shows our whole body impedance controller that basically with different mobility, you can assign different mobility when you want to achieve and reach a target in an autonomous way. On the left side, you have the mobility of the base mostly. On the right side, you have the combined mobility. At some point, you saw that the arm is moving, which is highly important when you want to ensure safety of the robot itself to avoid collisions and also safety of the people. And I will explain you how we are exploiting this. Some more videos on the MOCA whole body impedance control. On the left, you see the stiffness behavior of the robot while we are actually balancing the mobility coming from the robot fixed arm and the base itself. On the right arm, we are emulating actually a very low inertia. So you can see that we can move the entire robot by just a finger, small finger forces of a few newtons in the space, which can be really helpful for guiding the robot, teaching the robot, and things like that. This is the control interface of the robot. Now that we created this system, we can expand this shared control to a larger team, which can be several humans. And relying on what we built before, the robot can actually, through the vision system, also understand the intention of the people and bring the task to a space, to a configuration space which minimizes the loading, let's say, to makes it the most ergonomic possible, and also maximizes basically the interaction capacity of the person. And then we extended this to a situation that basically to understand who is your collaborative person and who is basically just an existing partner. Here, for instance, the robot, through our navigation and through our laser scanner and RGBD cameras, fusion of the sensory system, it understands that this person was not meant to be collaborate with, and therefore it just responds to the subject, to the person, to the worker that called MOCA to arrive to perform the task together. So This is a new concept we introduced. We call it HRC2, which is coexistent versus collaboration. Of course, we need to consider that not always we want to have direct connections with the robots. Most of the time, robots must coexist with people, and therefore all the avoidance, safety, security measures, which are highly important, must be still validated. We also, this is one of the papers we're presenting in this conference, also thought of maybe creating a supernumerary body where the humans and robots can physically couple in a very safe way to actually bring this shared control in a way smarter, but let's say stronger and with more endurance capacities. Of course, there's a sophisticated control behind. If you're interested, please go read the paper and watch the presentation online. But what happens here is through some gestures, you can call MOCA, which we call it MOCA man, and through some admittance interface, which is safe through some magnets here, you can clutch, attach very simply and very safely. And therefore, in that particular moment, robot becomes your supernumerary body. So you can exploit its different mobility through gesture, which moves the robot base only or the arm. Here, for instance, we are using gesture to change to the arm, and then you can actually, do whatever that you don't want to do with your own hand. Carry heavy objects, carry samples of the viruses that these days are very actually hot topics these days. You can actually interact with the environment that you don't want to do in real life. And of course, in industrial tasks, carrying high loads will be more important. And whenever you're done, therefore, you can really simply and easily just detach your arm. And what happens is that this robot can continue doing what it was supposed to do before. And in contrast with the exoskeletons, you can eliminate the variability times, all the times that you have to put it on, put it off, calibration needs and things like that. So this adds a lot of configuration and flexibility to our production systems as well. And it's also helpful, of course, when we were doing tasks manually and also by using MOCA man, we show that there is really high reduction of, let's say, not only loading, but also in most of the cases, other stimuli like vibration and things like that when you're performing the task. Again, highlighting the potential of MOCA man in industrial applications, maybe also in some rehabilitation that we are looking into in the near future. Then we started looking at the application of MOCA and this high-level intelligence and shared control in logistic applications. This is another paper we are presenting. This eye-graph that I'm giving a highlight for you is, what if humans and robots can work together in such, let's say, repetitive and such, let's say, effortful tasks that we have in warehouses. As you're not gonna believe it, but sometimes you see that robots in the videos moving in the warehouses and bringing boxes and things, but only 5% of the current warehouses worldwide are semi-automated. So we are working on these flexible systems to be able to do some, let's say, to automatize or semi-automatize these tasks that are currently happening in the warehouses. One example I quickly show you is that through some marker perception, you can understand what boxes you have, and through some optimization, you can optimize and maximize the number of boxes that you can put on a pallet. This is an online feature that we developed. By looking at the Aruco marker, we know how much is the weight and size of the object. Of course, the size can be also even from the vision perception system. And then when you have this information, you optimize it, and you can place the boxes in the optimized places to maximize the number of boxes on a pallet. So what happens here in the right screen that you can see, it also lets the human to contribute. It tells you, according to my calculation, you can move the small boxes that are less heavy, less bulky, and will have less risks on your joint. And sometimes even when the robot, since it has only one arm, can call for help to the human partner and actually telling that we are supposed to take it there because according to my optimization, we better put it there to maximize the number of boxes. Of course, we did it with human experiments. You can see it in the paper that this optimization gave the best, let's say, placement of the boxes in the pallet jack, where humans had to take it, bring it back, spend some more time to know how many boxes can be placed in the so everything that you see on the left side, which is the robot, is autonomous, with minimum pre-planning only by looking at the objects. So what's next? The next would be when the pallet is full, you can autonomously use the robot to move in a space, detect the pallet jack. Of course, we know roughly where the pallet jack is, but we don't know exactly where the handle is. This is same MOCA that approaches the pallet jack through the vision system, detects the pallet jack, and then starts through the whole body impedance controller that you saw in a couple of slides before. It detects it and moves it around. So the challenge here is that we have a highly underactuated system when they're coupled, because you have only 2 degrees of freedom, 1 rotational, 1 translational, plus all the dynamic uncertainties you have in the system. So the optimization and the planning becomes really complicated. We have a paper on this which is currently under review, and hopefully it will come out soon and you will be able to read this. So this also contributes to this task. My last topic that I would like to talk today is also teleoperation, which we saw some nice presentations before. It's one good example when humans and robots share their control to perform some complex tasks. So it all started with the concept of teleimpedance control that you see here, where we can control the impedance of the robot as well as its trajectories to regulate the endpoint stiffness of the robot based on the humans. So what you can do is essentially you can make the robot soft, interactive, safe. Imagine a scenario can be for these days, which is quite hot, to deal with the patients, to deal with the COVID patients, or at the same time you can increase the co-contraction, have a stiffer arm, and the robot will respond to that, and you can do high forceful or high manipulation, effortful manipulation tasks. And then we included some sort of, let's say, augmented reality to that to increase human awareness. You can see this shared control can be really helpful. Then in some cases, let's say that you see here, it provides a lot of information by simple gestures, and you can trigger some autonomous behaviors in the robot by simple gestures. Here we are detecting by looking at the recipe, we are understanding what material the person is selecting, and the robot is able to do that, to bring it for you. But it switches back to manual here. For instance, in teleoperation, you can pour as much as you want. By simple rotation, we can understand how much force, how much basically material pouring, but we put a force-torque sensor at the bottom, so it gives a real-time feedback. So these are really nice shared autonomy features that can help a lot increase the efficiency of the system, minimize human mistakes, minimize the number of times that you have to remember all the recipes or go back to the books and things like that to remember. So this is the recipe basically pinned at space somewhere. You go back to that and start basically looking at it, and this goes on and on, and you can see the data and information. Of course, this was too good not to implement it on our MOCA. What we did, we extended this through a whole body model that we have for the human, thanks to our ergonomics studies. So we used that model. We used the center of pressure model, which we use for ergonomics, to steer the robot movement, and we use the teleimpedance control, the video I showed you, to be able to control the robot movements. Here, the robot is moved back and forth, left, right, just like Segway, by inclining forward and backward. And the reason for that is we want to leave the arms free. And leaving the arms free lets you to do these kind of nice manipulation tasks only through the visual feedback, even in presence of some delay, of course, because the system is closed, is feed forward. We don't have the stability issues because we are providing impedance and position trajectories, and the delays will not cause instability in a sense of classical control. So you can see that here we are able to grasp different objects, perform manipulation, take the drill, and I want to go a bit faster, do the drilling. So if you're interested, we are also embedding some gesture features to understand in what direction the person wants to be stiff or what direction soft to be able to perform the task, and some valve turning and different manipulation tasks. This was too intuitive. A TV crew visited us, and immediately they were able to use it, just like using a Segway or something similar, so they were able to perform some tasks. I'm not sure if I have time, but just one last video I want to show is when it comes to interaction control, of course, what we want to do is to be able to catch the level of interaction from soft to stiff, but the most important thing is how to plan this. because at the moment, all of us, we are encoding, we are hard coding this interaction required. But sometimes what we can do, we can actually learn these interactions by exploiting and interacting with the environment. And this is the work we presented. It's actually currently an extended version of this under review. What I'm showing this here, the robots can interact with the environment. They can learn the viscoelastic properties and memorize them and embed these viscoelastic properties to the vision features that you extracted from the RGBD cameras. So the next time that you're performing a task, you know where to start and what stiffness behavior, what, let's say, quasi-static or dynamic behavior that you want to do to deal with the object. Even if, of course, you change the environment behavior, but the good thing is you're starting from a good guess, and then you can build and adapt on top of that good guess to converge much faster to the best interaction performance. And you can, of course, do some really cool tasks such as scooping or things like that. And of course, this requires also some intelligence. For instance, here, if you're colliding with the environment, you need some intelligence to understand this is a fault, to trigger a fault to come back to the system. I think that's my last slide. Yes, I would like to acknowledge, of course, the generous funding of our research in the lab from ERC and from Horizon 2020. If you're interested to know more about these projects, please take a screenshot and then look at the codes. I would like to thank you very much. If you have any questions, we have one postdoc position available at the moment. If you're interested, take a look at this and write me your application. Thank you very much.
Right, thank you, Arash. Very nice talk. We have a few questions, actually. One is from Antonio Franchi. So he thanks you for the nice talk again. And the question is this: if you had to extend these methodologies to aerial manipulators collaborating physically with humans, what do you think it could be kept as it is, and what should be further investigated and developed instead?
Right. It's a very nice question, actually. I mean, one of my dreams has been always to be able to extend this to aerial manipulation. Maybe we can already talk to Antonio, for instance. He's one of the experts in this area. I think the only problem is, Antonio and everybody else, if you agree with me, sometimes when we talk about collaborative robots, only co-carrying comes to our mind. So apparently, when we talk about physically coupled systems, there's not much many tasks that we think that in industry is happening. So it's mostly about sequential tasks that agent A is doing this, agent B is doing this, and sometimes you have this multi-layer approaches. There are like some sequences that you are physically coupled. I think it's important to actually consider not only physically coupled. I know that you've done a lot of nice works in co-carrying, things like that, but also in role allocation in terms of timing, maybe. When the human is there, when the flying, let's say, robot can take part of the task. And also, since with the flying robots, we have a larger workspace and more agility, maybe you can actually offload humans from a lot of these parts. And especially, I see a lot of good applications in logistics applications for moving the boxes around, collaborating with humans. If you're interested, maybe we can talk and have some joint work.
There's another question by Morteza Azad. I'm Morteza. So it says, in one of the presentations in the morning, we saw shared autonomy being taken care of as objectives in the null space of the main task. How do you see shared control versus shared autonomy, or as part of it?
Sorry, I didn't quite understand the situation, the question. So,
it says, in one of the presentations in the morning, yes. We saw shared autonomy versus, being taken care of as objectives in the null space of the main task.
Okay.
And so how do you see shared control versus shared autonomy?
Okay, so if you're meaning that shared control in the first objective and shared control in the null space object, to be honest, I'm not sure if these two are different, shared autonomy, shared control, because most of the literature, they use it one instead of the other. Correct me if I'm wrong, but I'm probably they are the same concept. I don't know, Serena, if you have some comments on this or anybody else.
Maybe if Morteza is there, he can clarify, yes. Because even for me, it's not super clear. The only thing
of course, maybe he meant that sometimes you have to do the shared control in the null space of the first task, of course, because of the priorities and things like that. Yeah. So if you're sharing something and this is your objective, it definitely should be your first objective. And sometimes you have other objectives that you need to share, but with lower priority. But the question is, if you have the same priorities and you can actually define them as an objective or constraint, what would you do? For instance, we saw a lot of manipulability. If you want to optimize manipulability and minimize the overloading joint torques that I showed, you can do vice versa. You can minimize overloading joint torques and put the manipulability as a constraint. So which one is better, which one not? At the moment, we don't have a question. We've been talking a lot about this. But of course, I think this is a matter of tuning. But hopefully one day we will be able to tune these automatically to have some rigid rules, some adaptive rules for selection of these parameters as well.
Yeah, I think in your case, maybe it was referring to exploiting the null space for everything that is related to optimizing, yes, for example, ergonomics or other things.
Of course, we are doing that because humans, as you saw in the videos, we had to optimize considering the null space, both for the human, because if the task is to drill there, then you need to give feedback to the null space of the human, how to do the task, but change your redundant degrees of freedom of the human to be able to do the same thing with minimum loading. For the robot, of course, for the fixed base robot, it doesn't make much sense. 1 degree of freedom is not going to change a lot. But if you have a mobile base, then the sky's the limit. You can actually move the base around. You can change a lot the workspace. In most of the works you saw, I showed you we have a null space controller, and this null space means the mobility as well. So you have 10 degrees of freedom, 7 plus 2 on the mobility, 7 plus 3 on the mobility, and then you can actually move the robot in space. That's null space control. So we have both sides of the same problem.
Okay, so I think we are almost on time, so maybe we stop and give play to the next speaker.
Thanks again.
Thank you, Arash.
Bye-bye.
Thank you.